Hello, everyone. Automatic coding of open-ended questions, so the text answers. Does double coding of the training data reduce the error of automatic coding? This is joint work with Sophie He, my former PhD student. So, traditionally, the text data collected from open-ended questions were manually coded. And of course, manual coding costs money, and we are considering automatic coding instead here. And what do we mean by automatic coding? We train a statistical learning model or machine learning model, same thing, on a small proportion of the text called the training data. And this small portion is, of course, still manually coded. And then we code the remainder automatically using the trained model. And we're saving costs because the remainder of the text don't need to be coded manually. Okay, so we're using the approach of creating n-gram variables from text here. N-gram variables are counts of how often the unigram or bigram, so the single word occurs in the text, or the sequence of two words occurs in the text. I don't have time to go into this other than to say, here's a small example. We're using stemming, we're removing frequent words, so-called stop words. We're using thresholds and all the usual things. Okay. So training data is, of course, still subject to error because human coders can make mistakes in their coding. And due to human error, or because the texts are ambiguous and therefore difficult to code, or because there's a gap in the coding manual, the point is there can be error. And that's why we typically double code a subset of the data and to assess the degree of disagreement or intercoder reliability, and usually this is measured by kappa. So if you already double code a subset of the data, maybe we can actually use the double coded data to use in statistical learning. And if so, how? But you may also not have the code, the data already double coded, the training data, and you may have a fixed budget. And in that case, should you go out of your way to double code the data, or should you just leave it single coded? That's the goal for this presentation. Now, when you have double coded data, it's not completely clear how you would use it for the purpose of statistical learning. And we are investigating 4 different strategies here. The first strategy, replicate, means that rather than having 1 observation per answer text, I have 2 observations per answer text, the first corresponding to coda 1, the second one corresponding to coda 2. So I just replicate, I double the training data. Then I have remove differences, which means, well, I'm suspicious of answers where the coders disagree, and I simply remove them from the training data. Third, there's majority vote. If any disagreements arise, and they do, then I employ a third coder who casts another vote, and then we are determined by majority vote. Expert resolves is very similar, except that the third coder is an expert who is very likely to be right, and is also much more expensive, or she. And here we assume that the expert is always correct. That is an assumption, but that works well for the simulation, and it doesn't destroy the conclusions. So here's an example. I have 3 texts coded, and coda 1 and 2 agree on text 1. The coding choices are A, B, C, and D, and here they agree on code C, and in text 3 they agree on code A. So for all the methods, this is carried through with an A all the way through and a C all the way through. The differences arise here where they disagree. Remove differences just throws this observation out. Majority vote employs the third coder who happens to decide it's C, and the expert resolves can do anything because he's the expert or she's the expert, including they could actually choose a different code altogether if they wanted. So I chose code D here just for an example. So then we have replicate, and you see that there are two observations per text answer, one coded by coder 1 and the other one coded by coder 2. And we just append one to the other and we get twice as many observations. All right, now one issue is that these different strategies have different costs. The cost of double coding is twice that of single coding. The cost of remove differences is still twice that of single coding because I first have to double code everything before I remove anything. The cost of majority vote is a little bit more than twice that of single coding, depending on for what fractions disagreements arise in the coding. The cost of expert resolves is much more, assuming that the expert costs much more than a regular coder. And we typically assume it's 10 times the cost of a regular coder. So we could do one of two things now, keeping the size of the training data constant. But instead, what we do is we keep the cost constant, because that seems more realistic. And for constant cost, then I can afford different number of texts to code, so the size of the training data varies. This is all in comparison to single coding, where we can afford n observations to single code. Replicate and remove differences, we can afford half as many because they are twice as expensive. For majority vote and expert resolves, we can afford fewer than half as many. And the exact number depends on the probability of a coding error, the P, the number of categories or outcomes that we can code, L, and T, which is the cost of an expert relative to a regular coder, here assumed to be 10 times the cost. All right, so I'm rephrasing the earlier goals into research questions. I'm now saying, assuming a fixed budget, which of the 5 strategies maximizes prediction accuracy for statistical learning? And the 5 strategies include single coding. On second, when the data are already double coded, which strategy maximizes prediction accuracy? And this might be true, as I said, because we want to compute kappa and we already have a data double coded. We did several simulations and applications to real data set, and for time constraints, I'm showing one. We simulated the 5 strategies on the patient Joe data and assumed that the codes available were true, the resolved codes that we had previously. And then we simulated an error rate from 0% to 50%. Now, when you have only 2 classes you can code into, like yes or no, or right or wrong or something, and you make an error, then it's very clear what class the error is, because if it's not the right one, then it's the other one, right? There's only 2. But when there are more than 2 classes, we have to decide where the error occurs, in what other class it occurs. And this is captured by this coding matrix M1 here, where we have the true code on the one axis, and on the other axis we have the predicted code. And if it were all on the diagonal, it would be all correct, but it's not always correct because we have an error P here. And that error P is distributed equally over the other columns here, which means that if I make an error, there's an equal chance of choosing any of the incorrect other categories. Now, this is sort of the simplest but also sensible option, maybe. If I have, I can think of more complicated options. So for example, if I have ordered outcomes, I can say if I make an error, then it must be one of the neighboring categories, so one higher or one lower, right? They're ordered. Or I can say, well, this is an optimistic coder, And the coder, if he makes an error or she makes an error, always codes into a higher class. And then I get something like this. Okay. So I'm injecting error into the resolved codes of a data set. This is the patient Joe data set. Joe's doctor told him that he would need to return in 2 weeks to find out whether his condition had improved. But when Joe asked the receptionist for an appointment, he was told that it would be over a month before the next available appointment. What should Joe do? So here's a bit of a conflict, and Joe can say yes, which is a passive reaction. Joe can insist that the doctor confirm that that is okay, which is proactive. Somewhat proactive is an intermediate choice, and counterproductive is if Joe stomps off and goes the next time to an emergency room or another doctor or something. Here are results. The right column here is under fixed budget, and the left column is when double-coded data are already available, so I don't have to pay for them. The first row is most interesting. This is the matrix M1 that applies in all situations. The second and third one are specific choices for the ordered outcomes. Okay, so what do we see? Single coding here is at the bottom, and here almost at the bottom. So if the double-coded data are already available and they're free, you don't want to use single coding. Instead, what you want to use is this purple dashed line, which is the expert resolves. Now, it makes sense that if you have an expert who's always right, and if you don't have to pay for the expert, then you would want the entire training data set be coded by the expert. That makes sense, and we see this bear out in the graphs. Now, this may not always be realistic, that the expert is always available to do all the work. So backing off of that, the second best strategy depends on which coding matrix you use. And if we focus on smaller probabilities of error, which are more realistic, 50% is really very high, right? Smaller percentages of errors, and we can see that the remove differences and replicate are equal in their strategies. However, that changes here depending on the other coding matrix. Now, turning to fixed budget, single coding, the gray line, wins each and every time for reasonable error rates. You know, if you get into high error rates, then strange things happen. So if we have a fixed budget and assuming the error rate is reasonable, single coding. So don't pay for the extra codes. All right. So, and I'm just summarizing my recommendations here. Fixed budget, use single coding, unless the error is really too big, and then you may want to look into why it's too big and change the coding manual or something. If the data are already double-coded and it's free, never use single coding, and instead use the expert resolves if the expert is available. If unavailable, then you want to use replicate or remove differences. There's sort of a minor exception here, which came out of a different paper that I haven't talked about. I will leave you to read this, but it's just a minor exception. Okay, so here we have some references. The paper is based on the first two talks, and the minor exception here would be in this first paper, and the general case of more than 2 outcome classes is here in the second paper. And there's some other papers. Here is more information of how to do the n-gram variables. All right. Thank you for listening.